Okay, so finally we have arrived at the jewel, the bit of Calculus 2 that is unambiguously important in big capital letters, at least if you intend to go on and do any sort of research in science or engineering or anything like that. So, in the previous section, we took advantage of geometric series to derive power series representations of elementary functions. Now, we want to ask if it is possible, in general, to take an elementary function and replace it with a power series. And in general, the answer is no. There are functions for which it is impossible to represent them as a power series. But the class of functions for which power series representations exist is still big enough to be super important in science. So what is this power series expansion going to look like in general? Well, let's just suppose for the moment that the function does have a representation. Well, it's going to have to look like this, right? Now, what happens when you plug in x equals a? Well, then over here we're going to get a minus a, which is 0, a minus a, which is 0. Every single term in the series is going to cancel out except for the first one. So that means this first coefficient is going to be f at a. All right. Now, let's assume that this function f can be differentiated infinitely. So you can differentiate it infinitely many times. So since power series can be differentiated just by applying the power rule to every term, let's go ahead and differentiate this equation and see what happens. So c naught disappears, and everything else is obtained just by taking the power rule. Now if we plug in x equals a again, all of these terms cancel out except for the first one. So c sub 1 is the derivative at a. Okay, well, let's keep on going. Let's differentiate this again. We apply the power rule again. Plug in a, everything cancels out except for this first term. So we get c2 is the second derivative at a divided by 2. Well, let's go again. And we get this. Differentiate again, and we get this. So looking at the formulas for the subsequent coefficients, we can see the pattern taking shape. That the numerator is always a derivative applied at the center point, and the denominator is a factorial, right? It's the product of all of the integers from 1 up to whatever the order of the coefficient is. And there you have it. That's how easy it is to arrive at the formula for the Taylor series. So the Taylor series expansion of a function is the representation of that function as a power series where the coefficients are given by this formula. So derivatives on the top, factorial on the bottom. It's called a Taylor series centered at a, or the Taylor series about a, whatever. If the center point is 0, then this is called a Maclaurin series. The mathematicians Taylor and Maclaurin, I don't know too much about them. I think they were from like the 1600s. They apparently did this work independently of one another. This idea of taking functions and replacing them with series. I don't know historically why it is that Taylor's name is associated with the general case, and Maclaurin's name is associated with the case where a is equal to 0, but, I mean, that's what we got. That's what the current notation is. So if we just take a partial sum of the Taylor series, we get what's called the Taylor Polynomial. So that's what we get if we just stop the series at some point. And then the kth remainder is the difference between the Taylor Polynomial and the actual function. Okay, the difference between the function being represented and the whatever Taylor Polynomial. Okay. So find the Maclaurin series of the function e to the power x. So the strategy that we were using in the previous section of taking the function and writing it so that it looks like 1 over 1 minus stuff, so that we could take advantage of the geometric series, that's really not going to work here. I mean, no matter how hard we try, we're not going to be able to make this guy fit the pattern of a geometric series sum. So we got to use this formula. I mean, that's really the only bit that you need to compute, because everything else in the Taylor expansion is given. We just have to compute the coefficients. Incidentally, since it's a Maclaurin series, the center point is 0. Okay, so we need to take derivatives. So what is the pattern in the derivatives? Well, differentiate e to the power x and nothing is going to change. So you can differentiate it as many times as you want, it's still going to be e to the x. So in general, the nth derivative is e to the x, and we need to apply it at the center point. So we're applying it at 0, so that's going to be e to the power 0, which is 1. Okay, so we get that the coefficients of the Maclaurin expansion are 1 over n factorial. So the Maclaurin expansion is just this formula where c sub n is given by, well, what we just computed. Right, and since the center point is 0, I don't need to... Yeah, this is correct. Now what about the radius of convergence? Okay? So recall the formula for the radius of convergence. That is c sub n over c sub n plus 1, where c sub n is, I mean, here, given just there. So this is so because we're dealing with factorials here, the absolute values have nothing to do. So I'm just going to do this a little more quickly, if you don't mind. Right, because dividing fractions is the same as multiplying by reciprocals. N plus 1 factorial is the same as n plus 1 times n factorial. So we just get n plus 1 left over. So taking that limit, we get infinity. Cool. So the radius of convergence is infinite, which implies that the Maclaurin series, this dude, converges for all values of x. So notice that I've been careful to not write that e to the x is equal to this thing yet. Because all we've done is we've just computed the Maclaurin series. We don't actually know if this dude is equal to e to the x yet. So we will establish that in a moment. But anyway, yeah, that's how you compute the series. You just compute the coefficients by taking derivatives and going from there. Now, notice that because this series exists and it converges for all real numbers, it must be the case that the individual terms of the series are going to 0, right? Remember, if a series converges, then the terms of the series have to be going to 0. So if we just isolate that fact, then we get this. So that's an occasionally useful fact. Okay, so is this expansion actually equal to the function e to the x? Well, let's see. If it is, then this remainder term, which is the difference between f and the partial sums of the Taylor series, this remainder has to be going to 0. Okay? So if the Taylor series actually equals the function, then this remainder has to be going to 0. That's basically what I say here. So how do we get any handle on the size of the remainder? Well, that's where Taylor's inequality comes in. So if the k plus 1th derivative is bounded by some number, for values of x within some prescribed range, so this is just an interval centered at a, then the remainder satisfies the following inequality. Now, notice that, this mk, this is a constant. So d to the k plus 1 over k plus 1 factorial, that's exactly the same form as this dude, right? So in the limit as k goes to infinity, this chunk is going to go to 0. The only sort of complication that might keep this from going to 0 is m sub k, where m sub k is a bound on the derivative, on the kth derivative. But that means that if this bound is actually not dependent on k, if this bound is universal, if you can find a number such that all of the derivatives are bounded by it, well then, this dude is just a constant. So then this fact applies, and this guy goes to 0, which means that the remainder is going to 0, which means that the function equals its Taylor series. Okay? So all we need to do to show that the function and its Taylor series are actually the same is to show that the derivatives are uniformly bounded. There is some number which bounds all the derivatives. That's enough. Now, this is actually a very strong condition, but for the sort of functions that we're looking at, it's going to be sufficient. Okay, so prove that e to the x is actually equal to this Maclaurin series. So we need to show that there is a number which bounds all of the derivatives for x within some range. Yeah. Okay. So we need to show... Okay, so let's start, because x needs to be within some range. So let d just be any positive number. For x for x satisfying, in this case it's Maclaurin, so a is equal to 0. So absolute value x less than or equal to d, we need to show that the nth derivative of e to the x is uniformly bounded for some number m. Okay, well, the nth derivative of e to the x is just e to the x. And it's e to the x is always positive, so the absolute values don't do anything either. Now let's see. We are restricting x to being less than or equal to d here. So since x is less than or equal to d, well, that's the same as saying that x is between negative d and d, right? That's how you can translate an inequality, or an absolute value into an inequality. So if x is within this range, well, what is the largest that e to the x could possibly be? Well, when x is equal to d. right? Because e to the x is an increasing function. So take x as far to the right as possible, and it's going to be the largest. So as long as we are restricting ourselves to the range absolute value x less than d, we have e to the x less than or equal to e to the d. That is, m is e to the d. And since this is the case for any derivative, that is a universal bound. So we conclude that, so since this inequality holds for all derivatives of e to the x, we conclude that e to the x is equal to its Maclaurin series. For this range. So as long as x is less than or equal to absolute value x is less than or equal to d, e to the x is in fact equal to its Maclaurin series. But wait a second. D was chosen completely arbitrarily. How did I start? I said just let d be a positive number. So e to the x is equal to its Maclaurin series on any finite interval. So that means it's always equal to its Maclaurin series for all real numbers. So yeah, just let d go to infinity. Right? Just let it get bigger and bigger and bigger, and the same conclusion holds for every choice of d. So that's very nice. So this is sort of the best outcome that we could have hoped for. So let me put that in a box because it is a very nice fact. So e to the x is in fact equal to this series for all real numbers x. So that is very cool. That is a very useful fact. In particular, notice what happens when we let x equal 1. Because when x is equal to 1, the left-hand side becomes e. So that gives us a series representation of the number e. Well, not an approximation, but an actual representation. So yeah, so if you actually wanted to compute e, this is one way that you could go about doing it. Just add up a bunch of reciprocals of factorials. And it's probably a pretty good approximation because, factorials grow extremely quickly. So that means that these terms are very quickly going to be shrinking to almost nothing. So just adding up the first few would probably give you a very good approximation for e. So I don't know if historically that's how they did it, but that would certainly work. Okay, so we know what the Maclaurin series for e to the x is. Let's compute the Taylor series for e to the x at a equals 2. So now we have a different center point. And really, there's nothing to do but to, plug stuff into this formula again. Only now, instead of a equals 0, we have a equals 2. So c sub n is equal to the nth derivative. Now it's being applied at 2 over n factorial. Well, we know that the nth derivative is just e to the x, so that's e squared over n factorial. Just plugging 2 into e to the x. So the desired expansion is that. Okay, so here's the coefficients, and because the center point is 2 now, we plug that in. Incidentally, I haven't shown that e to the x is actually equal to this dude, but it's easy. It's the same exact procedure that we went through, so I will not go through it. And again, it holds for all x. The radius of convergence is infinity. Did I ever establish that? Yeah, radius of convergence is infinity for that dude. Okay. Find the Maclaurin series for sine x, and then prove that it actually equals it. That it actually equals sine. Okay, so nothing to do but to compute the coefficients. So to get the coefficients, we need to take a bunch of derivatives and then plug in the center point and see what happens. And a is equal to 0 because it's a Maclaurin series. So I should say this. So to compute the coefficients, we need to compute the first few. Well, nah. We can just go straight to it. So anyway, so the first coefficient, c0, is f, right? The first coefficient is literally sine at the center point. And what we're looking for here is we're looking for a pattern. So c1 is going to be the derivative at 0. So the derivative of sine is cosine. So that's 1. Cosine at 0 is 1. Okay, c2 is going to be f double prime at 0 divided by 2. So that begs the question, what is f double prime? Well, the second derivative of sine is, so first derivative is cosine, so second derivative is negative sine. So negative sine 0 at 2. Oh, wouldn't you know it, that's 0 again. Okay, for the next coefficient, we're going to need the third derivative. So the derivative of negative sine is negative cosine. So that means the third coefficient is going to be f triple prime at 0 over 3 factorial. So plugging in 0, we get negative 1. We just put the negative there. For the next one, we're going to need the fourth derivative, and we're just going to keep on going until we see a pattern. So derivative of cosine is negative sine, so negative sine is positive sine again. So plugging in sine of 0 gives us 0 again. So what's the pattern so far? 0, 1, 0, negative 1 over 3 factorial, 0. Yeah, I don't quite see it yet. Well, we're now at the point where the derivatives are going to start repeating themselves. So we get cosine again. So this is c sub 5. So cosine of 0 is 1, so we get positive 1 over 5 factorial. Okay, well maybe now you can see the pattern. 1, negative 1. So the sign is alternating. The denominator is all odd numbers. So the denominator here is 1 factorial, which is just 1, 3 factorial, 5 factorial. So indeed, that is the pattern. The pattern is that they are alternating, and we are getting 1 over the odd factorials. So let's go just one more time to really hammer that home, because the next derivative is going to be minus sine x again. And, plugging 0 into the sign is just going to give us 0 again. So all the even numbers, all the even coefficients have been 0 so far. And, that's just going to keep on happening. The derivative of negative sine is negative cosine again. So plugging 0 into negative cosine gives us negative 1 over 7 factorial. So indeed, you can clearly see the pattern now. The signs are alternating, plus, minus, and it's just 1 over the odd factorials. So in general, so the pattern is it's 0 if n is even, and then the coefficient is negative 1 to the n. Oh, that's not quite doing it either. I'm sorry, how about this? So let's just write it out. So let's just write it out. So 1 minus 1 over 3 factorial, and this is the third coefficient, so that means we have x cubed next to it. Like so. And then if we attempt to put a pattern to this, this is I just want to make sure that this agrees with what I do later. Okay, yeah. So to put a pattern on this, the following pattern will work. So it's alternating, so we definitely have to put an alternator there. And then the denominator is odd numbers factorial. Well, one way that we can always get odd numbers is by the formula 2n plus 1. Right? Because think about it. When n is equal to 0, you get 1. When n is equal to 1, you get 2 plus 1, which is 3. When n is equal to 2, you get 4 plus 1, which is 5, and so on and so on. So 2n plus 1 will always give you the odd numbers. And then that number is reflected in the exponent as well. So there you go. There's the Maclaurin series for sine. Now, to show that it is actually equal to the Maclaurin series, all we need to do is show that there is a universal bound for all of the derivatives. So actually, yeah, we don't even need to worry about the range stuff here because the bound in this case isn't going to depend on the range either. So it suffices to show that the nth derivative of sine x is less than or equal to m for some real number m and all x. Well, indeed, the derivatives of sine are always going to be plus minus sine or cosine. Of sine. And those just keep on repeating forever. And sine and cosine are always bounded above by 1. Right? I mean, sine is always between 1 and negative 1. Cosine is between 1 and negative 1. So take the absolute value, and then it doesn't matter if there's a plus minus in front of here. The absolute value will kill it. And so yeah, the absolute value is always less than or equal to 1. So that is our universal bound. And indeed, that doesn't even depend on a range of x's. That's going to be true for all real numbers. So anyway, that is sufficient to conclude that the sine function, much like the exponential function, is indeed equal to its Maclaurin series for all real numbers x. There is no restriction. Okay. So we're building up a catalog of series expansions here. We've got e to the x. We've got sine. Next, let's do cosine. So we could go through this whole procedure again by just computing the coefficients by taking derivatives. But because cosine is just the derivative of sine, all we need to do is just differentiate this power series. Or the Maclaurin series, I should say. So that's easy, because differentiating a power series is just doing the power rule. And because differentiation doesn't change the radius of convergence, we get that it is actually equal everywhere as well. So let's see. Right? So just bring down the 2n plus 1 and subtract 1. However, we can actually simplify this a little bit, because 2n plus 1 factorial is the same as 2n plus 1 times 2n factorial. So the 2n plus 1 cancels, and we actually get this. So what is the pattern here? Well, it's exactly the same pattern, only instead of having odd numbers, we have even numbers. Yep, it's exactly the same pattern, only with even numbers instead of odd numbers. Okay. So, what about the Maclaurin series for x cosine x? Well, once again, we could go through this whole procedure if we want, but that's going to be extremely ugly because we would have to be using the product rule at every step. So instead, let's just plug in the Maclaurin series for cosine and multiply it by x. So we get x cosine x is equal to x times the Maclaurin series for cosine. And then all we need to do is take this x and distribute it through, and that's just going to increment this exponent by 1. Like so. So that's it. That's all there is to it. So indeed, because the action of actually computing Maclaurin series and Taylor series it's very expensive. You have to compute a bunch of derivatives. It is always good to take advantage of the series that have already been computed. So yeah, take advantage of the series that you already have. Okay. Next, represent sine as the sum of its Taylor series centered at pi over 3. So over here, we found the Maclaurin series, so that's the center point at 0. Now we want the center point to be pi over 3. Okay? So unfortunately, there's nothing to be done here but to actually go through the procedure and compute the coefficients again. So this time the center point is pi over 3. Okie dokie. So here we go. So c sub 0 is just the function evaluated at the number. So sine of pi over 3 is that's the same as 60 degrees. So that's root 3 over 2. For all of the others, we need to start computing derivatives. So actually, you know what? Let me just take the work that we've already done. So only we are applying it to pi over 3 now. So cosine at pi over 3 is 1/2. Okay, sine at pi over 3 is root 3 over 2, so this is minus root 3 over 4. You know what? Let me write it like this, because I'm wary of doing any actual computations, because the computations might erode the structure of the pattern that arises. So anyway, what's cosine at pi over 3? That's 1/2. So minus 1/2. Like so. Sine at pi over 3 is root 3 over 2 again. See, but now it's got that 4 factorial there. Cosine of pi over 3 is 1/2. sine to the power of 3 is root 3 over 2 again. So we get minus root 3 over 2 this time. Like so. Finally, I mean, I think the pattern is becoming... I think the pattern is starting to show up. But let's go just one more. So cosine at pi over 3 is 1/2. So we have minus 1/2. Okay, so what is the pattern happening? Root 3 over 2, 1/2. 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 So it's constantly alternating between root 3 over 2 and 1/2. And then next to that, we have... Okay, so yeah. So the numerator is always alternating between root 3 and 1. The denominator is 2 times n factorial. And then the alternator is going positive, positive, negative, negative, positive, positive, negative, negative. So that's the pattern. So the expansion of sine x. So let's just write this out. So this is 0, 1, 2. Next is going to be 3. Next is going to be 4, so it's positive again. Next it's going to be well, I think you get the picture. And so on, forever and ever. Amen. So, yeah. So kind of ugly, but whatever. It's demonstrating the point that ultimately all you need to do this, all that you need to compute a Taylor series is just compute a bunch of derivatives applied at the center point. That's really all there is to it. So, ugly as it is an illustration of this principle. Okay, next. Find the Maclaurin series for that dude. So 1 plus x to the power k, where k is any real number. Okay, so nothing to do but to go through the procedure. And then see if we can figure out some sort of pattern. Okie dokie. So c sub 0 is just the function applied at the center point. Since this is Maclaurin, we have a is equal to 0. So c sub 0 is just the function at 0. So that's 1 to the power k, so that's 1. Now let's start computing derivatives. So the first derivative is k 1 plus x to the k minus 1, right? That's just power rule. So c sub 1 is f prime at 0. So plugging in 0, we're just going to get k. Second derivative, we're going to get k times k minus 1, 1 plus x to the power k minus 2. So let's see. If I plug in 0, this dude becomes 1. Well, okay, I mean, I think we can already sort of start seeing the pattern happen, because when we plug in 0, this latter term is always going to end up being 1. So we're really just taking the product of these terms that accumulate out in front of here. Over 2. But let's do a few more. So the next one is going to be k times k minus 1 times k minus 2 to the power k minus 3. So, as I said, plug in x equals 0, and it's just the accumulating k terms that are going to be kept. And let's do one more. So, what is the pattern? What is the pattern that's showing up here? I mean, the denominators are clearly all just the factorials, but there's a pretty clear pattern that's happening in the numerator as well. It's almost like a factorial. It's an interrupted factorial. In fact, this is the same as, well, if I were to keep on going, this would be k minus 4, k minus 5, k minus 6, blah, 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 right? So this is actually the same as k factorial, but all of those remaining terms got canceled out. They got canceled out by a k minus 4 factorial on the bottom. Right? I mean, just write this out. You'll see what I mean. Because k factorial is the completion of this statement. It's got a whole bunch of other terms, but you can imagine that this dude on the bottom is like canceling them all out. Well, same deal happens here. This time it would be k minus 3 factorial. Well, same pattern holds here. And 2 is the same as 2 factorial, so I just put that in there. So, do these guys look familiar to you? You've seen these before. I guarantee that you have somewhere, either in algebra or maybe in like a discrete math course if you've ever looked at that, or in probability and statistics if you ever took a statistics course. I guarantee you have seen these guys before. These are the binomial coefficients. So the expression k factorial over n factorial k minus n parentheses factorial, because that's what's happening here, is given by a special notation, kn, like so. And that is called a binomial coefficient. These guys show up all the time. If you've taken a statistics course, I guarantee that you've seen these. So yeah, this is a well-known pattern. So the general term, the nth coefficient, and this pattern does continue here and here if you want to verify that. So in general, the nth coefficient is literally just the binomial coefficient. Oh my god. Course is almost over. Still no better at typing. Alas, this is my lot in life. So the Maclaurin expansion is like so. So that's how you would write it down. Incidentally, what is the radius of convergence of this guy? Well, let's just go ahead and compute that. So this is absolute value of the ratio of the binomial coefficients. So let's see. So that's given by this formula here. So that's Cn divided by Cn plus 1. Yeah, so k is constant here, and n is what's being incremented. So k minus n plus 1 is k minus n minus 1, right? Yeah, because I'm replacing n with n plus 1. Like so. Okie dokie, so the k's cancel. So the k factorials cancel. N plus 1 factorial is the same as n plus 1 times n factorial, so the n factorials cancel. And that's left over on the top. As for this, so k minus n factorial, that's the same as k minus n minus 1 factorial, right? So how convenient, those guys cancel out as well. So we are left over with the limit as n goes to infinity. Oh, you know what? I actually do need the absolute values here because k is any real number, so k might be Oh, you know what? Oh, that's interesting. Because k factorial is only defined if k is an integer. Ooh. Yeah, that's tricky. That's tricky. So this formula actually isn't strictly correct. Well, whatever. Let's not worry about it too much. Yeah, let's not worry about it too much. This formula is just a shorthand for these formulas here, which are perfectly well defined. So, yeah, it's not that big a deal. Okay? It's a shorthand for these guys. Anyway. So what do we have left over? So these guys cancel. So I need absolute values around everything that has a k in it. But that's not too much to ask. That's not too much to ask. Okie dokie. So what do we have here? Well, we have a rational function. The degree on the top is 1. The degree on the bottom is also 1. So This limit is just the ratio of the leading terms, so that's 1 over negative 1. So that's negative 1. That's the absolute value of negative 1, which is 1. So anyway, radius of convergence is 1. Okay. So all of that was in the service of being able to do something like this without going crazy computing a whole bunch of derivatives, right? Because now that we have a general expression for the Maclaurin series of something like this, where k can be any real number, now we can do this, because this is 4 minus x to the power negative 1/2. So this expansion will work. So we do have to be a little bit careful. We have to make sure that this is in exactly the correct form before we just throw it in the Maclaurin expansion, because the existence of this 4 is giving me a little bit of trepidation. Yeah, so for this to work, the x has to be positive and this has to be a 1. So how can we fix this? Well, we can factor out that 4. Like so. Right? So I factored out that 4, which means I had to introduce a 1 over 4 instead. So 4 to the power negative 1/2 is 1 over 2. And then now I need this dude to be positive, but that's easy enough because I can just change this into plus and then there, like so. Okay? So this is going to be the binomial expansion with k equal to negative 1/2 and x equal to negative x over 4. Okay, so since negative x over 4 is taking the x position, I need to replace x with negative x over 4 there. Anyway, so let me actually write out the first few terms. So it's 1 plus kx plus this dude. See, I'm wary about using this formula now because it's not strictly correct. But all the same, it is the analogy is what causes them to use the binomial coefficients. I mean, in the book they write this, so that's clearly the analogy that they were going for. X cubed, and let's do one more. Okay, but then instead of x, it has to be negative x over 4. Like so. So this is one of the few cases where doing this on the computer is actually better than doing it on the board, because boy howdy, it would take a lot of time to write all of this stuff out if I didn't have if I couldn't just copy paste. And now k has to be -1/2. So let me begin copy pasting there as well. You know what? Hang on. let's put this on a new line. Because now I sort of want to start simplifying things. So negative negative becomes positive. Yeah, 2 times 4 is 8. Now, -1/2 minus 1 is once again going to be negative. So -1/2 minus 1 is -3/2. So those negatives cancel. This negative gets squared away over 4 squared Yeah, so let me write it like this so that I don't elide the pattern. Yeah, because it's going to be 2 times 4 to increasing powers. And this should actually be 2 factorial here. I mean, I know 2 is equal to 2 factorial, but again, I'm just trying to keep the pattern clear. Yeah. And then I'll simplify this again in another step. Anyway, so 3 factorial, 4 cubed, x cubed. -1 cubed is negative. So negative 1, 2, 3, 4 negative signs. So that's all going to be positive. So -1/2 minus 1 is -3/2. Minus 2, that's -5/2. Yeah, so 1, 2, 3, 4 negative signs. Those all got canceled. 2 negative signs. Those got canceled. 1 negative sign. No, 2 negative signs, so those got canceled. Okay. Yeah, so it seems like 1, 2, 3, 4 negative signs. Those all get canceled. Yeah, so it seems like it's all going to be positive. Yeah, so this gets 4'd away. 1, 2, 3, 4, those cancel. Yep. So -1/2 minus 3 is 7/2. Okay, so I mean, we can pretty clearly see what the pattern is here. I mean, the pattern is definitely taking shape. So let's just go one step further to really nail it home. And also to get rid of those horribly, horribly ugly fractions. So here we got 2 squared. So 2 squared is going on the bottom. So 2 factorial. Incidentally, okay, so 4 is the same as 2 squared as well. So this is 2 to the 4th times another 2 squared is 2 to the 6th. And then 1 times 3. So 4 is 2 squared, so that's 2 to the 6, and then 1, 2, 3, so that's 2 to the 9, powers of 2 altogether, 3 times 5, whoops, this is x cubed. 4 is the same as 2 squared. 2 times 4 is 8. Then 1, 2, 3, 4 more powers of 2. So 8 plus 4 is 12. So there's this interesting odd-numbered factorial that's starting to take shape in the numerator. It's like a factorial, but only with odd numbers. Okay. So yeah, so there's the pattern. Incidentally. So 2 times 4 is 8, so that's 2 cubed. And just to keep the pattern alive, I should say 1 factorial. And I can make that even more extreme. Say 0 factorial right there, because 0 factorial is 1. Interesting. So yeah, so the powers of 2 are increasing by 3, because this is 2 to the power 0. Right? Right? Because that's just 1 again. So 0, 3, 6, 9, 12. Cool. Yeah, that's neat. There's a nice pattern there. Okie dokie. So here are all of the Maclaurin series that we have computed thus far, either in this section or in the previous section. So here is the ordinary geometric series. Here's the exponential, sine and cosine. I have the radii of convergence here as well. Arctan we did in the previous section. Natural log we did in the previous section. And then here's the one that we just spent a good 20 minutes, half hour, I don't know, talking about. Okay, so let's just do a few more examples. So find the sum of this series. Now this is interesting. Up until now, we've really never asked you to straight up find the actual number that a series sums to, unless it's a geometric series. But in this case, we actually can. And the trick is just recognizing that this guy matches one of these forms up here. In particular, it matches this guy with x equals 1/2. So notice that this is so if I just rewrite this slightly, this 2 to the n in the denominator, I can rewrite to look more like this, like so. And now, wouldn't you know it, this is exactly the formula for natural log 1 plus x, where x is equal to 1/2. This is the Maclaurin series, I should say. Incidentally, this is perfectly valid because the radius of convergence is 1. So if we're doing the Maclaurin series, then the center point is 0. So 1/2 is indeed less than 1 away from 0. So this is valid. So this series is just natural log 1 plus x with x equals 1/2. So that's very cool. We are actually able to get a number for an infinite series, which is something which is honestly pretty rare. So 1 plus 1/2, so that's natural log 3/2, whatever that number is. So that's what this series sums to. It sums to natural log 3/2. Pretty cool. And, as we saw in the previous section, once we have power series expansions of things, taking derivatives and antiderivatives becomes trivial, because you just have to do the power rule at every step. So, e to the negative x squared, this is an example of a function that we literally cannot antidifferentiate in terms of elementary functions, but in terms of infinite series, I can antidifferentiate this guy no problem. So replace e to the negative x squared with its Maclaurin series. Well, in particular, how do we do that? Well, let's take the Maclaurin series for e to the x, but instead of x, we put negative x squared. So let's take the Maclaurin series for e to the x, which was this dude. But instead of x, it has to be negative x squared. Like so. So let's clean this up a little bit. Because this negative to the power n ends up being an alternator. And then we are left with x to the 2n. So now we just take the power rule. Right, so add 1 to the exponent and then divide by that. So there you have it. And don't forget the constant of integration. So, pretty easy. And just for fun, let's see what this actually looks like just by writing out the first few terms. So this is, when n is equal to 0, we're going to get x. When n is equal to 1, so 2n plus 1, remember 2n plus 1 is always the odd numbers. So it's alternating, and we're going to get odd powers and odd numbers in the denominator. And there's going to be a factorial hanging on as well. So here we had 0 factorial, which is 1. Here we have 1 factorial, which is 1. Next, we're going to have 2 factorial. And the next odd number is 5. Yep. So that's a nice little pattern. It always feels good, I think, to see these patterns taking shape. Okay, so now let's use this to evaluate a definite integral. So pretty much all we need to do is just, well, I say it as if it's simple, but just evaluate this dude at 1 and at 0. So when we plug in 0, it's pretty clear that everything's going to disappear. When we plug in 1, and let's put in a few more, why not? Odd numbers, so the next one would be 9. Okay, so this definite integral is equal to this infinite series. So how many terms of this series do we need to get an error of 0.001 or less? Well, this is an alternating series, so we can use the alternating series estimation theorem. Okay, now in the previous section, I went crazy trying to do the alternating series estimation theorem. I was being pig-headed. Here's the thing. Here's all the alternating series estimation theorem says. It says that if I take, say, the third partial sum, if I add up the first 3 terms, the error is bounded by the next term. If I take the first 4 partial sums, the error is bounded by the next term. If I take the 5th partial sum, the error is bounded by the next term. Okay? So I want the error to be smaller than 0.001, but the error is given by the terms themselves. So really, I just need to figure out what the first term is, which is smaller than 0.001. And then I add up all of the terms up to that. Let's just start actually writing out the decimal approximations of these things, because I want to see the first one, which is less than 0.001. So yeah, that stuff that I was doing last time was pig-headed, stupid. This is much better strategy. What was I doing? Oh yeah. Sorry. Keep doing that as if by habit. So here I am just computing these things in my calculator. Okay, so the next one would be 4 factorial times 9. So not smaller than 0.001 yet. So 5 factorial times 11. Okay. Okie dokie. So this is the first one, which is smaller than 0.001. is the 1, 2, 3, 4, 5, 6th term. We need to add up the first 5 terms to get the desired accuracy. So, adding up just the first 5 terms, we get, I'll be there in a moment. There we go. So that's that. Okay, so finally, I just want to show how we can multiply 2 power series together. So find the first 3 non-zero terms in the Maclaurin series for this dude. So once again, we could go through the whole procedure of computing a bunch of derivatives of this thing, but that would require us to take the product rule at every step, and that's going to be very, very ugly. So instead, let's just plug in the Maclaurin series of those 2 guys and multiply the first few terms. Because all we need is the first 3 non-zero terms. So let's see how that's going to work. So e to the x is this. And actually, let me put in the expanded form. And then sine x is this. Okay, so of course, these 2 guys go on forever, but we are only interested in the first 3 non-zero terms. So let's see. First off, we would have to take 1 times x, 1 times this, 1 times this, 1 times this, and so on and so on and so on, right? If I were to take the 1 and distribute it all the way through. Plus, I would have to take this and distribute it all the way through. Then I would have to take this and distribute it all the way through, right? So it's like I'm taking an infinite sum of infinite sums. But in order to do this maybe more systematically, let's focus on the degrees of the terms. So first off, let's see if there's going to be any constant terms. Well, no, there aren't going to be any constant terms, because the only constant term here is 1, and then I'm going to have to multiply that, but no matter what I multiply it by, it's going to end up having a larger degree. So what about degree 1 terms? Well, let's see. One way that I'm going to get a degree 1 term is by taking 1 times x. So that's a degree 1 term. Next, I would have to take 1 times this, but that's a degree 3 term, so that's too big. Next, I would take 1 times this, but that's degree 5, so that's too big. And everything after that point is going to be too big. Okay, so move on. X times x is going to be x squared. Well, that's too big. X times x cubed is going to be x to the 4th. Well, that's too big. And so on and so forth. So there's only one degree 1 term, namely 1 times x. What about degree 2 terms? So 1 times x is x, already got that. 1 times x cubed is x cubed, that's too big. 1 times x to the 5th, that's too big, and so on, too big. X times x is x squared. Okay, that's a degree 2 term. X times x cubed is x to the 4th, that's too big. X times x to the 5th is x to the 6th, that's too big. Okay, it's going to keep on being too big forever. So there are no other degree 2 terms. Degree 3 terms. So 1 times x, already have that. 1 times x cubed. So that is that's a degree 3 term. What about any other degree 3 terms? So 1 times x to the 5th, that's too big. 1 times x to the 7th, that's too big. All right. X times x to get x squared, already have that. X times x cubed to get x to the 4th, that's too big. X times x to the 5th, that's too big, and so on and so on. X squared times x. Aha, that's a degree 3 term. So that's x squared over 2 factorial times x. So that's x cubed over 2 factorial. And since these are both degree 3 terms, I can combine these. I can combine the like terms, right? So x squared times x, that gave us another degree 3 term. X squared times x cubed, well, that's x to the 5th, so that's too big. X squared times x to the 5th, that's too big, and so on and so on. X cubed times x, well, that's x to the 4th, so that's too big, and so on and so on and so on. So there aren't any other degree 3 terms. Let's simplify this, because this is 1/2 minus 3 factorial is 6, so 1/2 minus 1/6 is, common denominator is 6, 3 minus 1 is 2, so that's 2 over 6, so that's the same as 1 over 3. Okie dokie, so there we go, there's our first 3 non-zero terms. And we can keep on going, but, you know, we don't need to. So x squared 1/3 x cubed. Okay. So yeah, just focus it in terms of degrees, and that'll allow you to attack an infinite problem systematically. Okay, so I know this was a long one. I hope you broke it up into chunks, because I certainly wouldn't want to sit through this whole thing all at once. All right, so that's it for this one.